Counterfactual reasoning is essential for safe planning and diagnosis in embodied AI. But most causal models rely on global monotonicity, a structural assumption that shatters the moment you introduce contact, friction, or context-dependent dynamics. If you drop that restriction, do you lose the ability to identify counterfactuals from data? This video breaks down new research from East China Normal University that answers this question with a resounding no. The authors introduce non-monotone triangular structural causal models, proving that global monotonicity is not the essential ingredient for identifiability. Instead, you need mechanism-wise invertibility and context-independent inverse transport. We'll walk through the theory of exogenous isomorphism, the CausalInverter architecture, and the MuJoCo benchmarks that reveal a sharp boundary between where structured causal priors dominate and where flexible baselines catch up. Let's start with the setup. We're working with triangular recursive structural causal models. The endogenous variables follow a fixed causal order, so each variable is a function of its predecessors and an exogenous noise term. This triangular structure gives us a well-defined solution map from exogenous space to the observed variables. The standard approach to counterfactual identifiability in this class relies on global monotonicity. The idea is that if the mechanism is globally monotone in the exogenous variable, the solution map is injective, and you can uniquely recover the exogenous code via abduction. This guarantees that observationally equivalent models are counterfactually identical. But in embodied systems, global monotonicity is often violated. Consider a contact interaction where the same exogenous perturbation might push the system in opposite directions depending on the parent state, like the contact angle or pose. A classic example is a mechanism where y equals SGN of x times uy. Here, the orientation flips based on the context x. Global monotonicity breaks, yet the system is still physically deterministic. If we remove structure entirely, we fall into counterfactual ambiguity. So the question is, what structure remains sufficient once global monotonicity is dropped? The authors propose a class called NM-TM-SCM. This retains the triangular recursion, but relaxes the mechanism constraints. The key insight is that counterfactual identifiability hinges on a property called exogenous isomorphism. Two models are exogenous isomorphically equivalent if they share the same latent worlds up to a coordinate change in the exogenous space. This is the right semantic criterion because it ensures that the same hidden physical realization, like a specific friction variation or microgeometry, is tracked consistently across models. The theory establishes a sharp chain of equivalences. First, mechanism-wise invertibility ensures that, for any fixed parent context, the map from exogenous to endogenous variables is a bijection. This guarantees unique factual abduction. Second, and this is the critical condition, is context-independent inverse transport. If you have two observationally equivalent models, the transport between their inverse maps must not depend on the parent context. If the inverse transport is context-independent, it defines a fixed coordinate transformation between the exogenous variables of the two models. This implies exogenous isomorphism, which in turn implies complete counterfactual identifiability. The authors prove this is sharp. They provide a counterexample showing that local invertibility alone is insufficient. In the sign flip example, two models can be observationally equivalent and locally invertible, yet disagree on counterfactuals because the inverse transport depends on the context x. This context dependence allows observationally equivalent models to silently relabel the latent physical world differently depending on the state, breaking counterfactual agreement. So how do we operationalize this? The researchers instantiate the theory in a model called CausalInverter. The architecture is built around a structured parametrization. For each mechanism, the model predicts a context-dependent shift, a context-dependent orientation gate that can flip sign based on the parents, and an invertible monotone scalar flow. This allows the model to express parent-dependent sign reversals while maintaining mechanism-wise invertibility. The training objective includes the standard negative log likelihood for observational modeling, augmented by two stabilizers. First, a cycle loss ensures the forward and inverse maps are consistent. Second, and most importantly, a transport stability regularization term penalizes the variance of the learned inverse transport across different parent contexts. This explicitly enforces the context-independent inverse transport condition, turning the theoretical guarantee into an active model design constraint. The experiments validate this approach across synthetic mechanisms and physical interaction tasks. On synthetic benchmarks, the authors test globally monotone mechanisms, threshold flip mechanisms, and smooth flip mechanisms. When the mechanism is globally monotone, all structured baselines perform competitively. But once parent-dependent orientation flips appear, the advantage of CausalInverter becomes clear. Baselines like additive noise models and monotone triangular SCMs fail to reduce counterfactual error, while CausalInverter sharply drops the error and recovers the orientation field with high accuracy. To probe the boundary further, the authors run a continuous non-monotonicity bridge sweep. As the calibrated non-monotonicity score increases, the counterfactual advantage of CausalInverter over monotone baselines grows systematically. The gain tracks the non-monotonicity score with a slope near 1, confirming that the structural bias is specifically valuable when branch-sensitive reversals become common. The physical evaluation uses MuJoCo interaction tasks, push, and door. To compare tasks, the authors introduce a composite non-monotonicity score based on the context flip ratio and contact ratio. Door exhibits strong non-monotonicity, while push is a weak non-monotonicity boundary case. On the door task, the results are compelling. CausalInverter achieves perfect event-level counterfactual recovery on the formal split. More importantly, in a multi-seed head-to-head against the strongest compact learned baselines, including a transformer sequence model and a conditional flow dynamics model, CausalInverter delivers substantially more stable event recovery. The transformer achieves perfect accuracy on the single split, but with a very narrow safety margin, and its event accuracy drops significantly across seeds. The conditional flow model achieves lower continuous geometric error, but misses a non-trivial fraction of event labels. This highlights a key distinction. Continuous error metrics do not always correlate with counterfactual branch correctness. CausalInverter preserves the correct event branch reliably, even if some baselines achieve slightly better continuous geometry scores. On the push task, the story is different. Push has a much lower non-monotonicity score. Here, CausalInverter remains competitive, but does not dominate. Linear dynamics and MLP world models achieve similar or better performance on both continuous and event metrics. This is not a failure of the theory. It reveals the bias variance trade-off. In the weak non-monotonicity regime, the structural bias of CausalInverter can be overregularizing relative to more flexible state predictors. The structural constraint is most useful when the task contains strong branch-like structure that makes the counterfactual path genuinely ambiguous. Push marks the boundary where the inductive bias ceases to be the optimal trade-off. Ablation studies on door confirm that the context-dependent orientation gate is the dominant component, followed by transport stability. Removing these components causes severe degradation in counterfactual error, consistent with the theoretical requirement for stable exogenous alignment in the presence of orientation flips. To summarize, this work expands the identifiable regime of triangular structural causal models. It shows that global monotonicity is not necessary for counterfactual identifiability. Mechanism-wise invertibility combined with context-independent inverse transport is sufficient to guarantee exogenous isomorphism and complete counterfactual identification. This framework accommodates the context-dependent orientation, reversals common in embodied interaction. Empirically, the CausalInverter demonstrates that structured causal priors can outperform black box world models in strong non-monotonicity regimes, providing reliable event-level branch recovery and stability. The results on MuJoCo also provide a nuanced view of when these priors are most effective, identifying a clear boundary between strong and weak non-monotonicity tasks. This work offers a principled path toward counterfactual reasoning in complex physical systems, where simple monotonic assumptions no longer hold. For the full proofs, implementation details, and the balanced counterfactual sampling protocol, check the description. If you're interested in the latest research on causal AI, make sure to follow the channel. Thanks for watching.